Welcome, everyone. I'm in a little different position than normal. Normally, I'm in my home office, and tonight I join you from my car on the road, but all is well and everything is fine. I'd like to say thank you for joining us. For those who don't know me, I'm Professor Sean Tavalia, founding member of the board of the Hamptons Observatory and academic chair for physical sciences at Suffolk County Community College. On behalf of my fellow board members and colleagues at Suffolk County Community College, I would like to welcome everyone to tonight's presentation. For those of you who are unfamiliar with our organization, the Hamptons Observatory was founded nearly 20 years ago with a mission to provide free, year-round, family-friendly educational events that focus on science and the natural world. After the presentation, please visit the Hamptons Observatory website to learn about our future presentations, join our email list, or donate to help ensure that we can continue providing these incredible opportunities for everyone. If you feel so inspired by tonight's presentation, this will be my shameless plug to tell you to please visit Suffolk County Community College, where you can begin your journey into a scientific career at one of our three campuses in Brentwood, Selden, or Riverhead, or in some cases from the comfort of your own home with our online offerings. As we begin tonight's presentation, I ask that you keep your microphones muted. Please feel free to post questions in the chat at the conclusion of the presentation. We'll do our best to address all questions, and depending on how it goes, may just ask you to unmute and ask them on your own. Tonight's speaker is a professor of astrophysics at the City University of New York's College of Staten Island, an associate with the Department of Astrophysics at the American Museum of Natural History, and president of the Astronomical Society of New York. His research focuses on starburst galaxies, supermassive black holes, and the star formation history of the universe. In 1998, he joined the Hayden Planetarium's scientific staff, where he helped develop the design, exhibits, and scientific content of the Rose Center for Earth and Space Sciences, one of my favorite places to be. In 2020, Dr. Liu was named a Legacy Fellow of the American Astronomical Society, and in 2024, he was awarded the AAS Education Prize, which celebrated his national and international impact as an astronomy educator. Dr. Liu is host of the podcast, The Luniverse with Dr. Charles Liu, which is in its fifth season and has been a frequent guest of Neil deGrasse Tyson's podcast, Star Talk. In addition to his research publications, Dr. Liu has published 11 popular books about astronomy and science, most recently the handy Quantum Physics Answer Book and The Cosmos Explained. He, Robert Iron, and Neil deGrasse Tyson were awarded the American Institute of Physics Science Writing Award for their book, One Universe at Home in the Cosmos. We are so delighted to have you join us, Dr. Liu. Please, the floor is yours.
Thank you so much. If anybody has any technical issues hearing whatever, please by all means put it in the chat so that we can address it as quickly as possible. We already have a slight hiccup in the sense that when I'm trying to share my entire screen, it's cutting off part of the screen. So I'm just going to share this window, and so you can see all the cool things on the top and so on, and then we'll just talk through and have a good time. I'll be switching back and forth anyway between this window and other windows because there's some videos and pictures I'd like to share that are not on the slide deck. So if you have any questions, by all means, put them in the chat. I will try to answer them as appropriate. My goal is to talk for about 40-ish minutes, maybe a little more, maybe a little less, and then open the floor to questions because that's really where the fun part begins. I also have a little bit of a vested interest in ending on time today. The talk part at least. Questions go on forever because outside my front yard right now there is a Meade 200 LX200 telescope waiting for me with family members gathered because later on this evening as it gets dark, two comets might be visible up in the night sky, two that are kind of low. One's Comet Swan, the other's Comet Lemon. They are about 9th, 10th magnitude, so not at all visible with the unaided eye, but with a telescope we just might be able to catch them before they set about 9 o'clock this evening, 8:30 thereabouts. So if you guys have nothing better to do after this, I encourage you to pop on outside and see if someone's got a telescope and see if you can take a look at this beautiful comet that will be visible going forward in the course of the month. So hopefully tonight will not be the only opportunity for you to take a look. Anyway, the trillion pixels a night refers to the Vera Rubin Observatory, right? What does that mean exactly? Well, you think about your cameras on your phones, for example. They probably have around 10 megapixels, right? That means it's maybe 3,000 by 3,000 pixels for each picture. So you get about 9 million or 10 million pixels in your pictures. Now, a trillion pixels is a million pixels. So imagine getting 100,000 photos of the sky every night. Okay, and these aren't just pictures you take with your camera, but these pictures are taken with a telescope that's more than 30 feet across and that has the ability to look down to the precision of little tiny, what we call arc seconds, right? Very, very, very small spaces. That is the Vera Rubin Observatory, and we're going to be looking with this telescope starting very soon on a systematic survey of the entire night sky as visible from northern Chile. But before then, we've already taken a lot of cool images and taken a lot of interesting data, found some cool stuff, and I'm here to tell you a little bit about that. I have served on the Science Advisory Committee for the Rubin Observatory for a few years now, and I'm very proud to be one of hundreds of scientists and thousands of people overall who have helped make this decades-long journey possible so that we're now on the brink of running the most prolific scientific survey in the history of astronomy. All right, let's go and give you a basic sense of why we want to do this, right? If I can get the screen to work. If we want to go and try to figure out what's happening in the universe, the first thing we want to do is take a look at it, right? The second thing we want to do is see if it changes at all. The whole point of that is, well, we think the universe is just there, right? The sky just stays the same. Well, it doesn't actually. It keeps changing. One night to another, you can see the moon moving across the sky. It's not where you think it was last night. It's in a new place. If you watch very carefully, there are little tiny things that look like stars, and we call those planets, of course, and they move every day, a little bit compared to other previous places. So astronomers have always wanted, it'd be great to just take a look and keep watching it. Watch the sky change. Watch the sky move. Watch the sky evolve in front of our eyes. But we can't do it. It's just too hard. The things that happen out in the universe don't usually take a few hours or a few days or a few seconds. They usually take years, decades, even millions of years sometimes. For example, the stars to move from their positions now compared to elsewhere, right? What they were in the past. So what's going to be the result? We look, we come back the next night and look again. For a few seconds or a few minutes at a time, we can't see that much change. Right? But what if we could look in the sky not just once, but keep taking pictures of them? As the Earth turns, we rotate the telescope ever so slightly every few minutes, and we take pictures and after picture after picture, and then compare those pictures over the course of the entire night. Then we can start seeing changes, right? But then what? The problem with that, of course, is that the changes, they're very faint. The things that are nearby in our universe don't change that much over time. The changes instead, what you're going to see is a flash here, a flash there, as for example, a star explodes, or a little bit of a motion here or there as an asteroid moves across the sky. But we can't see them because they're too faint and they're too few. So what are we going to wind up doing? If we get a big enough telescope that we can see a large enough piece of the sky, that we can do all of those things all at once, then we are getting somewhere. And if we can look for not just a few nights, not just even a year, but a decade, then we have pictures after pictures after pictures. That will make us happy. My technology continues to fail me, and it's probably my own fault. So I'm going to switch over to look at a couple of things that we're going to try first. Okay? This is a picture, which I'm going to share now, of the person that we care about. Okay? This is a picture from 1938. This person to the far left, I don't know if you can see my cursor, is Vera Rubin. She's 10 years old. She lives in Philadelphia. Vera Rubin was born in 1928. These are relatives of hers. And when I was giving a talk at the end of August at the New Jersey State Museum in Trenton, it turned out that one of Vera Rubin's cousins came to the talk. And she shared with us these pictures. That cousin, she's one generation younger. This woman on the far right was her mother. And her mother was first cousins with Vera Rubin. Vera and Ruthie were the two sisters that lived at that time. And this is a picture, like I said, taken in 1938. And this is the origins of when we make amazing observatories and telescopes, the people that, just like you and me. This is a picture from Philadelphia. It's a tremendously fortunate thing that that person was there. And so I was able to be in touch with her and be able to communicate, which is lovely. Now, this is a picture that comes later. Vera Rubin as an adult using equipment, looking not through digital cameras, but through various film photographic systems to try to measure different aspects of the motions of stars and the things in galaxies. All right. Vera Rubin, as you know, possibly, is the woman who confirmed that there was so much more material out in the universe that we cannot see, that emits no light or no electromagnetic radiation of any kind, that it is still influencing with its gravity the motion of the parts of our galaxy and other galaxies, so that they spin at the rates that they do. Okay. So Vera Rubin's careful monitoring of the motions of objects in the universe helped us confirm the existence of what we call dark matter. Right? For every pound of matter in the universe that gives off light, there are 3, 4, 5, maybe even 6 pounds of additional material that are not made up of protons and neutrons and electrons, that do not give off electromagnetic radiation of any kind. We cannot detect them with our telescopes except through the motion that they affect of the luminous matter. Okay? And so Vera's work was extremely important to us all. And she was a pioneer in many different ways. You can imagine that in the 1960s or so, she was one of the very few professional women who was doing astronomy or hard sciences of any kind. She suffered a significant amount of sexism and a lot of barriers to entry, but she persevered and pushed through anyway and was very successful, was a mentor and a role model for many, many women in astronomy today. Today, there are more women PhD astronomers and astrophysicists than there are men who are of that same academic rank. Vera was a big part of that. And she continued to advocate for the expansion of astronomy for lots and lots of people, not just men or women, but for anybody who wanted to be part of it. And she really opened the universe and the study of it to a lot of folks. And we have honored her as a nation. If you have, can you guys see this quarter? How many of you guys actually have a quarter? You can raise your hand hitting the icon if you have a Vera Rubin quarter. I finally got a Vera Rubin quarter in my so a friend handed it to me actually. I haven't gotten one in change yet, but they are in circulation. And so this is on the back of a US quarter, and you can see that it says United States of America over here, dark matter, right? and then this is Vera looking up in the sky in the future. So I think it's very cool. All right, let me see if I can get that technology working so that you can see more of what I'm talking about than what I'm just talking about. Let's see here. This is slide number 1, and then I am bummed. Why is it not doing this? You want me just to wave my hands, or you want me to keep trying? This is what I'm going to do, everybody. I'm going to go to my videos. All right? So the videos will still be worth it. The Vera Rubin Observatory is here, and I'm going to go through some galleries of pictures so that you can see what I was going to show you, but it's not going to be in a beautiful slide deck. It's going to be in a stack of pictures at the observatory's website. Please, everybody, go to the website and see these things. In a moment, we're going to see these views, the first look images from the Vera Rubin Observatory. Okay, and you see that's the NSF-DOE Rubin Observatory, the National Science Foundation of the United States, and the Department of Energy of the United States provided huge amounts of support, hundreds of millions of dollars over a couple of decades to make this happen. But this is a truly international program. Contributions have come from Chile, from the United Kingdom, from France, from Germany, from all of the European Space Agency, in fact, and also numerous other countries and observatories, institutions all over the place. What that means is that this observatory is for everyone. All of the data that's coming from this will wind up being available for literally everyone to use. And I'm very excited to say that because I want you all to use it. Okay, everybody should use the observatory if possible. Let me see now. I'm going to move the strip of stuff that's blocking my view, and then now put in back to rubinobservatory.org. Whoops, not RU. rubinobservatory.org. Everybody can follow along on their own computers in the future if they want to do this. And so you can see where we are here, bringing the night sky to life, all these different things that you can see, okay? About the Rubin Observatory here, this is the telescope that we're referring to. And if you look here, that is the observatory when it was still under construction and not quite finished. Right? It kind of looks like a star base on a distant asteroid, doesn't it? And in fact, the cylinder up top, which holds the telescope there, is about 40 feet across and 8 stories tall. And then there's the side information, all that stuff on the side there that looks like the rest of the spaceship. And that actually contains computers, electronics, technical things, and the internet connection, the servers that allow the data that come from this telescope to travel all over the world every night so that they can be analyzed quickly. Okay. So the construction schedule here, I want to show you explore the technology that's here. All right. And you can see this sort of stylized version of what's there. First of all, let's look at the mirror. That's where the mirror is here before it's installed in the telescope. Look how big it is compared to the human beings that are working on it. Okay. But this mirror has not just one mirror in a piece of glass. It literally is 2 mirrors in a glass. Can you guys see right here how you have this little edge? Oh man, where did that picture go? You know, I should not try so hard with this. We've already been figured out that the technology is not too happy, so I should try to keep it simple, right? Let me try to keep it simple. All right, let's go back to this and just show this. Right along the edge here, if you can see my cursor. Actually, Sean, can everyone see my cursor? Is my cursor visible at all? Okay, it is visible, so that's good. So you can see right along the cursor, notice that there looks like an edge, doesn't it? The picture inside that edge looks different from the picture outside that edge. Indeed, this mirror, which is about 30 feet across, is a single piece of glass that has one mirror built in on the inside, and then there's a mirror built in on the outside. It's shaped kind of like a salad bowl that's got an extra divot on the inside. And what that means is when you put that mirror up on the telescope, it not only uses one optical unit, but it has two. And then at the top of it, there's another. So the telescope light bounces off 1, 2, 3 times before it gets to the camera. And that allows you to see much more in the sky than you otherwise would be able to. I'll show you what I mean. We'll use Vera Rubin again. Everyone can see Vera Rubin's eye on this quarter. Okay, now imagine taking a quarter and holding it all the way out at a distance of 8 feet. Okay, so have somebody else across the room hold that quarter, Vera Rubin's quarter, and then look at Vera Rubin's eye. Imagine, if you will, how big that patch of sky is. Well, that patch of sky is about as big as a typical 8-meter telescope, or say the Hubble Space Telescope, is able to see at one time. Most of the time, you're not going to be able to see much of anything. Think about the cool pictures you see from telescopes today, like the Hubble. And they have so much detail, even in that tiny, tiny patch of sky. Okay, the actual width is a few arc minutes, right? But if you hold the whole quarter up at a distance of 8 feet, the actual width of the quarter is about a degree. And you can actually, with the Vera Rubin's multiple mirror structure in this same piece of glass, able not just to see as much as the area covered by Vera Rubin's eyeball, but actually be able to cover 2 entire quarters worth. All right. In other words, more than 200,000 times the area of the Hubble Space Telescope is what this Vera Rubin Observatory telescope can see at one time, thanks to this revolutionary technology, which has never been tried before in a big telescope like this. Okay. So the next thing, it's the largest digital camera in the world. Remember I was telling you about the trillion pixels a night? This is the size of the camera here. Okay, it's larger than a human being in both dimensions. It's extra long, actually. It sits in the telescope. It has 3,200 megapixels in one picture. It has 189 chips all at once. Every time you take a picture, you get 3,200 megapixels. And that's why when you take a picture every minute, all night, you will wind up getting more than 1 trillion pixels a night. And all of this together is put on the largest, fastest moving telescope mount for a telescope of this size. Many of you have telescopes, and you know that when you're moving a telescope, it's going, it takes time. But this can move from one observing location to the next in 4 seconds and stop steady enough to observe again. Okay. That's really the technology that we're talking about. It's quite amazing, and I really want you to see all of it when you get the chance. And then lastly, I want to mention this auxiliary telescope. This telescope is small. Some of you might actually use a telescope about this size at a college telescope observatory or something like that. But this telescope is called the auxiliary telescope, Auxtel. It used to sit in Arizona at Kitt Peak National Observatory. An acquaintance of mine, friend named Edgar Smith, helped finance and build that telescope for his research. And when he was finished with his research work, they took that telescope apart. He donated that telescope to the Rubin Observatory, and they brought it here. So even though it's small, it's extremely important. Here's the big telescope in the background, and you have this one here, and this one allows you to see what the sky is like during the time. When you're there trying to figure out what the sky is doing, then you can see the weather, you can see things changing, so that the computer-controlled systems inside the big telescope can modify the optical path ever so slightly using actuators or using thermal controls so that you can have the maximal imaging quality across that entire huge area of observation. So it is quite an amazing thing. Even though it's small, it really is necessary. And Calypso was the name of the telescope when Edgar Smith donated it to it. So big telescopes are good, but so are small ones. And I want you to remember that also, because you may be looking through a small telescope on Long Island or something, but you know what? That's okay, because that's important. So, legacy survey of space and time. I'll talk about this and I'll start showing you some videos. The legacy survey of space and time is the 10-year mission where the Rubin will be taking the images every night for a decade. This is that movie. It's a time-lapse picture of the entire sky. Viewed from that location, you can catch the southern hemisphere all the way down. You can all the way see the center of the Milky Way galaxy and the supermassive black hole at the center, Sagittarius A star. You can look north a lot of the way. You can't quite get all the way to the North Pole, but you can get above our skies here at night. So you're doing pretty well overall. Okay. And so you're having a huge amount of pictures of the sky. And the observatory here is showing you how you're going to take these pictures. Boom, boom. While you're taking one picture, you're recomputing the other pictures. Another picture can be in progress. The other pictures are scheduled. You see how this is going back and forth and back and forth. This is not your usual, oh, let's point at a telescope object this way. And then a little while later, okay, let's go to that next telescope object. Then let's go to the next telescope object and so on. But this has actually been set up very carefully. The cadence, we're calling it, right? The survey cadence has to be established long ahead of time. And our scientific negotiations on how to do this observation, the cadence, has been going on for years. Because you have different cadences if you want to look for supermassive black holes, for example, than if you want to look for exploding stars, than if you want to look at new discovered asteroids. So all of these different cadences have to be balanced in order to use this telescope maximally. And getting all those trillions of pixels night after night after night gives you the opportunity to provide this legacy survey, right? Where the legacy will be sitting out in the internet or on servers for anybody in the world to use. You can imagine that even if every professional astronomer in the world, there may be, 8 or 10,000 of us at most, were to do all of our work with the LSST, everything that we wanted to do with all of our research, with those trillions and trillions of pixels every night going on for a decade, there's still going to be a huge amount of discovery space that's still available. So you and I, all of us, if we want to study an area of the sky using the LSST, we are allowed to, because this is a publicly funded international project, and the data will be made available after it's been processed and used to the general public. There may be a little bit of a time delay, but there's still so much to see that you could yourself just go and dial up stuff. You get an account on the Rubin Science Platform, it's called, and then you can start making discoveries yourself. Not to mention, every single night, what if Rubin finds a flash here and a flash there? A star has just exploded. A new asteroid has just been discovered. We need to follow that up right away. You need to go take a look as fast as you can. So telescopes all around the world every night will have an opportunity to look at newly discovered transient objects out in the universe. And you can go take a look, and might be possible for you to be the first person or the first observatory in the world to follow up a Rubin alert discovery. All right, this is cool. And I want everyone to feel that they are part of it. All of you in the audience now, if you want to make a scientific discovery, I am confident that over the course of the LSST for the Vera Rubin Observatory, you will get that chance. And because it's your taxpayer dollars at work, you don't have to pay. You can just go and do it. All right? So make sure to do that. So now is the good time for me to go and tell you about the observatory itself. Again, let me express my apologies that my technology has made it impossible for me to show these to you in a beautiful slide deck thing that's set up. But nevertheless, it will still be pretty. Okay, here's the first movie that we can see. This picture is just of one section. See, notice how it is zooming all the way across this area of the sky, right? It just keeps on going. Each one of these little notches represents a square in the pictures taken using that 3,200 megapixel camera, right? I am going to try to scroll off of this picture and then get you guys to the video that will scroll for you. Let's see where we've gone here. Look at the cosmic treasure chest. There's the original picture. And if I can scroll, you're looking at 1.4 Rubin's field of view. Here's the picture, and we can watch this. If you want to watch this after, or if the technology isn't working very well here, you can see it on YouTube. You watch it zoom. The more you zoom in and out, the more details you can see. You realize that that galaxy there isn't just a blob of light or a spirally thing. It has streamers of matter connecting individual galaxies back and forth. This is an expression of the dynamism of what's going on inside this cluster of galaxies. Those streamers of light going back and forth are representing hundreds of millions of years worth of motion of stars in those galaxies. These may be galaxies that are passing by or through each other, or possibly even on a collision course. And as the stars are streaming past each other, they're stripped away from their orderly spirals or disks or ellipticals into these streamers that look like tails and loops and whirls and things like that. That was just this cosmic treasure chest showing one small area of one nearby cluster of galaxies. And then all those other little dots behind that are galaxies that are as far as 10, 11, 12 billion light years away. Okay. I'm going to switch now to rhythms in the stars for just a second. And this is an example of the time domain observations that are being shown. Take a look eventually in this movie at these little round circles, right? Obviously the blue circles aren't in the sky, but they're marking stars that Rubin has observed over the course of many nights to have changed their brightness. They're pulsing. Our eyes might not be able to detect them that way, but the observatory can, the telescope can. I'm going to play this video now and you can see what I mean. So there's a star. I mean, if I were just looking up in the sky, I would never be able to tell. But you look at that star, and over the course of several observations, you can see that this star gets slowly dimmer and then brighter, right? 30% brighter in just a few hours. Going to another star over here, we see what's going on is that here's a star again also. Look how much fainter it is on May 2nd. And then it's 11% brighter just 12 minutes later, right? Imagine if our sun got 12% brighter, 11% brighter in 12 minutes. That would make for quite a sunburn, right? Here again, in just half an hour, it got 30% brighter. These stars are pulsing, and you can see that the symbolic way that those circles are pulsing shows you just how much change there actually is in the sky that a telescope system like the Vera Rubin Observatory can easily detect, but we, watching with our eyes, cannot. I'm going to go next to number 4. I'm saving a swarm of new asteroids, number 2 for last, because I think it's cool. But I want you to see the Lagoon and Trifid nebulas. If you guys have watched old Star Trek episodes, you'll recognize this nebula, this one over here. Okay, because anytime the Enterprise was hit by a Klingon thruster thing or whatever, it would shake like crazy. And if there was an alien in the way, they would show on the screen the Trifid Nebula spinning at a rapid rate to show that we are on this ship and in trouble, right? But the Trifid and Lagoon nebulae are actually clouds of gas and dust, and in some cases, bright, brand new stars embedded in these glowing clouds. Okay, these different colors of gas, they're real. Okay, if our eyes were as sensitive as the Rubin telescope, we would see these colors. Of course, they're not, so either all we see are like bright or not bright. But if you take a look at this, the blue light is usually caused by reflections of starlight onto grains of dust or metal, flakes, that when it shines toward us, it reflects only the blue light in our direction and leaves the red light behind. It's the same effect, roughly, that atmospheric molecules in Earth's atmosphere scatter light around and cause our sky to look blue in the daytime. That scattering is what creates this blue stuff around the outside. But the red light in here is caused by hydrogen molecules that get stripped of their electrons. And then when those electrons fly back and recombine with those hydrogen nuclei, then this red light is emitted in a particular color. And so that color indicates that there's enough intense radiation to ionize hydrogen gas. And that is a sure sign that there's something going on in there, probably the birth of brand new stars. So this is looking at an object in our solar system. I'm going to show the video, and you can see what the Rubin Observatory can see, which is something that none of us can see, but it's really cool to see and to study. So there's the bright stuff, the red indicating intense new star formation, the blue indicating reflections, and you can see for scale how big the moon is compared to this picture. Right? And we're zooming in to the nebula, and you can see right in the corner there how that dark stuff, which is dust-laden interstellar gas, those concentrations within them are where new stars are being born. That's not a nothing patch. That's a something patch, heavily obscured, which allows us to see what's going on. We get some hints of what's going on in there because around the edges of the dark clouds, there's that reddish glow from hydrogen alpha emission, right? Which indicates that, wow, there are new stars being born in there. All right, and the final video I want to show, a swarm of new asteroids. Let me set this up a little bit before we actually watch the video. When the Rubin was first designed, one of the ideas it would do is if you looked specifically in the area of the asteroid belt around our sun, we should be able, just by taking picture after picture, to find all kinds of new asteroids that are too faint for us to see with small telescopes. But if we are monitoring the asteroid belt well enough, we may be able to find hundreds of new asteroids a night. Okay? We know that there are supposed to be millions of asteroids in our main asteroid belt, but only some thousands have been discovered up to this point because we just can't maintain the ability to find them. So in the Rubin first look, this past year, there was an experiment done where for a period of nights, we looked only at the asteroid belt area where known asteroids were, but looked kind of between them to see if we can find any new asteroids. And the results were amazing. In fact, I'll tell you the results with words after we see this video. Seeing and finding the asteroids in the asteroid belt using Rubin turns out to be a beautiful and really, really neat sight to see. So there's the difference between a star, a galaxy, and an asteroid. And why? It's because over the course of several observations, you can see the asteroid moving across the sky compared to those other objects. Here are more. In just one picture alone, you can see all these asteroids dancing across the sky. And look at that. Over the course of several nights, astronomers were able to put a movie together showing all the objects that they found. Within 5 nights, 7 nights, let's go to the top, 2,100 new main belt asteroids were discovered. And that was only in that tiny sliver of where we know the asteroid belt to be. So in that main asteroid belt, if that tiny little sliver shows 2,000 asteroids in a week, do a little bit of arithmetic, turns out that by the end of the 10-year mission, we will have discovered 5 million new asteroids in our solar system. 5 million, right? Remember I told you that there were only 10,000 or so professional astronomers. Even if we spent our lives studying them, we wouldn't be able to study them all. But you can. If you want to study them, these asteroids will be found. They will be located, and their data will be available. And if you want to study them, if you want to learn how they move, if you want to learn whether they're spinning or not, if you want to learn how they're doing things, if they're going to wander, do you think that their asteroids are going to hit the Earth someday? Things like that. We can find them. It's going to be amazing. There's a special area with the Rubin Observatory where they're going to set up to look for near-Earth asteroids. If there is an asteroid that looks like it can approach us and might actually hit the Earth, we'll be ready, thanks to the Rubin Observatory. There's still a lot more to do, but that's kind of where it is. So I want to stop there by showing you that's what we have done so far. This is what we can continue to do, and I hope that all of you will take advantage of this tremendous opportunity, thanks originally to Vera Rubin and her inspiring work, and to the hundreds of astronomers and engineers and scientists, and for that matter, accountants and writers and logistics people and mechanics and everybody that contributed to all this project over the years. It is poised to be able to do amazing stuff. I'm happy to answer any questions beyond this, but I want you guys to really think about whether you want to do work with the Vera Rubin Observatory, because it's available. And with a little bit of effort, you too may be the person that is the next Vera Rubin, that inspires the next generation of science. And it's because of this observatory and all the work that so many people put into it. So thank you very much for that. Thank you much for your time. And let me answer some questions about it. Thank you all also for being so patient with the technological issues that didn't quite work out, but hopefully we were able to get something fun out of this anyway.
Yeah, you did a great job despite the technical difficulty. So thank you. That was wonderful. There's no questions in the chat at the moment. If anybody does have a question, feel free to you could raise your hand and that'll bring you right to the top of the list in the participants. You can get that under the reaction button at the bottom of your Zoom panel there. But I'll ask a question because it's just amazing to me that we have a telescope with a 3,200 megapixel camera.
Yes.
And I'm just wondering about the file size. Just looking at that server space, that would be amazing.
Yes, indeed. The file servers, one of the really neat things about the Rubin Observatory is that it has not only opened frontiers for astronomy, but it's also opened frontiers for data science. We are collaborating, well, not only with universities and supercomputer and computer science programs all over the world, but even with the largest corporations like Google and Amazon Web Services to be able to handle these files, right? Each file, as you rightly noted, Sean, is more than 3,000 megapixels, right? And so if you are counting terabytes, right, that's 15 terabytes of data every night. And if you know how fast a typical internet connection works, you can't get a fraction of that out from the telescope in one night with an ordinary internet connection. So a lot of what the building that you see down there is based on the infrastructure, the ability to store or cache the data while it's being sent out, right? In the meantime, what is being sent out? We still need to send out information. If a star explodes, we want somebody with a telescope at the nighttime to actually be able to observe it immediately. So we want to send them that information. So as the telescope's data come off of the camera and into the servers, they're immediately undergoing a first look,
Mhm.
and they get a glance to see what changed between it and the previous several observations. Once you get that difference, then you send that difference information, which has much smaller file size, out to the data centers. We call them alert brokers all
Mhm.
around the world. There's going to be one in California, there's going to be one in Chile, there's one in Germany, there's one in France, I think there's one in the UK, and they will then serve further that information out to the rest of the world, piece by piece, layer by layer. So the things that you want to know within minutes can go out right away. The things that can take a few more minutes or a few more hours or even a day or two will go out more slowly over time, so that eventually, by the end of a week or so, the observations will all be sent out.
That's a great idea. It's just an amazing idea. Um, and I'm assuming behind that is a lot of machine learning on the images.
Very much so. Right now, I actually got an email from a friend of a former student of mine who just said, "Yes, hey, we're working with a nonprofit special like academic organization using AI to try to do scientific work. Um, we'd like to give it a try on astronomical data." And how we get access to astronomical data that we can try to use the machine learning to figure out and find new things. And I said, hey, we got this Rubin Observatory. We got things to talk about. It is going to require
Yeah.
already a lot of that is happening. Every year, the Rubin Observatory has a full community workshop. Our most recent one happened in August, where different groups give presentations and tell us on their progress and what they're doing. And the entire data analysis and distribution group had 4 or 5 sessions filled hour after hour with this is what we're doing to deal with this kind of data. This is what we're doing with that kind of data. This is how we're sending that out. This is how we're learning whether or not that's actually a real thing or whether or not that's just a accidental splitch in the sky
Mhm.
or in the electronics. And yeah, there's a lot of that to do. So if you're interested in that aspect of science, the data aspect, the imaging aspect, there's room for you to do that too. I would strongly encourage you to be involved.
So there was a question also about, I think that's from Donna actually,
Mhm.
knowing that, there'll be places for citizen science with all this data. If somebody finds something, how do they report it?
Great point. The Rubin Observatory itself has within its website excuse me, um, has a thing where you can post your results. Okay, so someone says, I took one of your alerts and I found that there is indeed a star that's growing fast in brightness over the past several minutes in this location. Everyone go take a look if you want. So there's like an internal server that's moderated. Excuse me.
Mhm.
At each data center, there will also be these kinds of running chat rooms, kind of, almost like Discord servers, that will be running over the course of each night for people to announce their things. And then the astronomical community has things that report results over the course of longer periods of time, such as the minor planet circulars that are based in Cambridge, Massachusetts at Harvard. There are various gravitational wave detection things. There are gamma ray burst networks. Um, every once in a while, if you're hanging out with a bunch of astronomers, suddenly you'll hear like 4 or 5 beeps go off at the same time in different people's pockets, and they pull out their phones and say, "Oh, excuse me, I gotta run. They just found something," and they all dash over and try to see what they want to detect. So there's a lot of those things that will be fed into by the Rubin Observatory, as well as Rubin hosting that kind of real-time feedback mechanism.
And I believe you already answered, but there was one question about where the observatory is located.
Ah, the observatory is located in northern Chile in an area called the Alta Plana, the high plains. It is an area where, thanks to the way that the wind blows around the world and the South Pacific in particular, there is very, very little rain. In fact, on the mountaintop where the Rubin Observatory is actually located, um, I believe called Cerro Pachon, it has rained in the past decade less than an inch. So the goal is to be able to observe as much as possible in the dry, empty space. And it's kind of hard to access, but it is possible to get close. The Altiplano is actually a very remarkable landscape. It's barren, it's so dry. There are some places in that area where rain has never been recorded. There are places where highways are paved not with asphalt, but with salt because it's so dry that rock salt does a better job being a road
Yeah.
surface than the stuff that we use, the black stuff. That's all gooey when it's got too much sun. So these are amazing areas to look, and that's basically where it's located.
There was only one other question, and that's a question of would you be willing to share your presentation?
Ah,
If so, we could combine that if you reach out to Donna.
I I
We could
will gladly email the PowerPoint file for you guys to see.
awesome.
My guess is everything that I showed is already on here, but it might be a little bit more compact and you guys can use it more effectively in the
Yeah,
future.
that'd be
Yes,
wonderful. Thank
thank
you.
you all again for being so patient with the electronics not working. Hopefully, we were able to paint the pictures with words and with the website stuff to get you a sense of this amazing observatory.
The good news, Charles, is that you win awards for a good reason. You're a fantastic presenter. Your enthusiasm is wonderful. You paint a wonderful picture of the universe and everything that you do. I really appreciate it. It was,
Oh, thank you so
despite
much.
the technology, it was a wonderful presentation.
Thank you very much.
Yes, and
All
there's
right.
no more questions in there. So thank you, Charles. We really do
You're welcome.
appreciate it. We're so happy that you joined us tonight. We love being able to spread your knowledge to the rest of the people who joined us,
Oh,
and hopefully we'll see you again.
thank you. You guys did all the hard work, and I really appreciate that. Now get out there. If you have a telescope, you may want to look for those comets. I'm going to dash out and see what's out there. But I'm going to bundle up because it's like the first cold night of the year, right?
Right?
Whew.
It's autumn is here.
Okay. Thank you again, everybody.
Have a good night, Charles.
Good night. Good night.
Good night, all.